Hello, welcome to another module in this massive open online course. So, let us continue our discussion in the application of SVD, singular value decomposition, for MIMO wireless communication, and let us specifically look at MIMO optimization, that is how to optimize the performance of the multiple input multiple output wireless communication system. Okay. So, we want to look at an application of SVD, and more specifically we are looking at how to optimize the performance of the MIMO wireless communication system. And so, what we have seen so far in the previous module is that applying the SVD, you can take the MIMO system. Once you apply the SVD, this becomes your decoupled, correct? Decoupled MIMO comprising of the T parallel channels, right. So, that is applying the MIMO using the pre-coding at the transmitter and the post processing combining at the receiver. You can convert this coupled MIMO system into a decoupled MIMO system comprising of T parallel channels, and then therefore, we had seen that essentially implies that you can multiplex or simultaneously transmit T symbols over the same time and frequency, and this therefore leads to spatial multiplexing, right, you remember. Okay. So, you can recall that this is what we had termed as spatial multiplexing, right. And each of this channel is given as, if you can recall, that is we have xi tilde that is being transmitted through a channel with gain sigma I, and then you have the noise which is n tilde I, and you have the output which is basically your yi, right. That is essentially what we had seen here, right. Yi tilde is the output, and this is there for I equal to 1 to up to t, okay. And the sigma I, you can see what is this sigma I. This sigma I is basically the amplitude gain, right. The power gain will be gain in the power or the SNR will be sigma I square. The model is yi tilde equals sigma I xi tilde plus n tilde I. Let us now assume that the transmit power of the ith symbol this is equal to expected value of magnitude xi tilde square, let this equal to pi, let us call this pi, and let us call the noise power as sigma square. This is the noise power. So, the output SNR for the ith channel this will be equal to, because we have the amplitude gain sigma I. So, we will have a factor, the gain of the power will be sigma I square, sigma I square times the input power, which is Pi, divided by sigma square, which is the noise power. Okay. So, that is the output SNR for the ith channel, sigma I square Pi divided by sigma square. This is the output SNR for the ith channel, which implies the maximum rate from the Shannon formula, which implies the maximum transmission rate for error free decoding, which is given by the Shannon capacity which is given as log to the base 2 1 plus SNR I, which is essentially, now if you substitute the expression for, so this is essentially your Shannon capacity formula, right. This is the well known Shannon formula, which is given as, therefore, substituting the value for SNR I. So, you have sigma I square Pi divided by sigma square. Okay. So, this is the maximum rate I for the ith channel. And now the sum rate, so this is the rate I for each channel I, and therefore, the sum rate is given as, is basically obtained by the sum of the rates of these individual T channels, all right. So, therefore, the sum rate, this is equal to summation I equal to 1 to T R I, which is summation I equal to 1 to T log to the base 2 1 plus sigma I square Pi over sigma square. This is the maximum, this is the sum rate, and now we want to maximize this sum rate. We want to maximize the sum rate. Now, typically, whenever we look at a wireless communication, there is a constraint on the transmit power, right. The transmit power is not unlimited, right. So, which essentially implies that this, if you look at all these T parallel channels, right, which have powers P1, P2, Pt, the total transmit power has to be constrained by a maximum power. That is, if you look at summation, that is P1 plus P2 plus so on up to Pt, that has to be less than or equal to the total transmit power. Let us call this as P naught, right. So, typically we have the total transmit power, that is, if you look at the powers of these T channels, P1 plus P2 plus so on up to Pt, this has to be constrained to be less than or equal to P naught. You can call this as the total transmit power. You can call this as the total transmit power. So, this is the total power constraint. Right. So, this implies that you will have summation I equal to 1 to T Pi is less than or equal to P naught, and therefore, the optimization problem for Mimo rate maximization, this can be formulated as the optimization problem for rate maximization, that will be maximize, right, sum I equal to 1 to t the sum rate log to the base 2 1 plus sigma I square pi divided by sigma square subject to the constraint I equal to 1 to t pi less than or equal to the total power p naught, and this is again we have a constrained, if you remember this is a constrained optimization problem, all right, summation of pi less than or equal to p naught. So, we want to maximize the sum rate, that is the sum of the rates, sum of the transmission rates Ri across the t parallel channels, all right, that constitute this Mimo channel subject to the power constraint, that is the total transmit power, that is summation pi has to be less than or equal to p naught, which is the total transmit power. And as we have seen several times before, the way to solve this constraint optimization problem is to introduce the Lagrange, construct the Lagrangian using the Lagrange multiplier lambda, right. So, we construct the Lagrangian and what is the Lagrangian? That is, if you look at summation I equal to 1 to t log, this is the optimization objective, log to the base 2 1 plus sigma I square pi by sigma square times 1 lambda 1 minus summation I equal to 1 to t pi, or in fact summation lambda p naught minus summation I equal to 1 to t pi. So, this is the, if you recall, this is the optimization objective and this is the constraint, and therefore, now this is a function of your, this is basically this is the Lagrangian, and now we have to take the partial derivative of f with respect to. So, the condition, the KKT condition is that the gradient of f has to vanish, which implies that the partial derivative with respect to each pi, this has to be equal to 0, right, for I equal to 1 to up to t. So, this implies, now you differentiate this with respect to pi, this implies that 1 over log 2 to the base e times differentiate this sigma I square over sigma square divided by 1 plus sigma I square pi over sigma square minus lambda equal to 0. This is the condition you get when you take the partial derivative with respect to pi and basically set it equal to 0. Okay. And when you solve this, you will get the condition. This implies basically that pi, solving for pi, you will get pi equal to 1 over log 2 to the base e times lambda minus sigma square over sigma I square, and here I will introduce this plus because the power has to be positive, non-negative, right. So, where this x plus equal to x if x is greater than or equal to 0, 0 if x is less than 0. Okay. So, this is this quantity 1 over log 2 to the base e times lambda minus sigma square, that is the noise variance, divided by sigma I square, which is essentially the power gain, the gain of the channel, and sigma I, you recall, is the ith singular value, and this plus essentially is to indicate that it can be this quantity only if it is non-negative, right. If it is negative, then the power cannot be negative. So, you have to set the power equal to 0, all right. So, let us recall these different quantities. Sigma I square, this is the noise variance, and if you recall this sigma I equals ith in fact this log 2 to the base e lambda, you can set it as a parameter, you can simply call this as lambda tilde, okay, because this is just a parameter. So, you can call this as 1 over lambda tilde minus sigma square over sigma I square plus, okay, and this is for I equal to 1 to t, where lambda tilde equals log 2 to the base e times lambda. And how to find lambda tilde, and of course, now we ask the question how to determine lambda tilde. Remember, we still have the power constraint. So, we have summation I equal to 1 to t pi is equal to p naught, which implies, now substitute for the expression for pi, summation I equal to 1 to t 1 over lambda tilde minus sigma square over sigma I square, this is equal to p. So, solve this to determine lambda tilde, okay, 1 over lambda tilde, that is the summation of the powers, all the transmit powers must be equal to p naught, which is the total transmit power. Okay. Now, this, if you see, this has a very interesting structure, this power allocation, if you see, this has a very interesting structure. This is known, that is, if you plot this power allocation, you will realize that, let us first plot the different quantities, the different bars. Okay. Each of these bars is of different height. This is of height, this is of height sigma square by sigma 1 square, this is of height sigma square by sigma 2 square sigma square by sigma 3 square sigma square by sigma sigma t square. This is the last bar. Now, remember, sigma 1 singular values are arranged in the decreasing order, sigma 1 greater than or equal to sigma 2 greater than or equal to sigma 3, so on greater than or equal to sigma t, which implies sigma square by sigma 1 square is less than or equal to sigma square by sigma 2 square is less than or equal to sigma square by sigma t square, right. So, this bars are in increasing order of height, right. Sigma square by sigma 1 square is less than or equal to sigma square by sigma 2 square, so on and so forth, is less than or equal to sigma square by sigma t square. Okay. Now, if you call 1 over lambda tilde as this level, if you think of filling this bowl with water, and if you call 1 over lambda tilde as the water level, right, it is convenient to think of this 1 over lambda tilde as the water level, okay. Then the power allocated Pi is the height of the water level, right. So, Pi P1 equal to 1 over lambda tilde minus sigma square over sigma 1 square. This is equal to P2 equal to 1 over lambda tilde minus sigma square by sigma 2 square. And now you can see, if sigma square over sigma t square is greater than the water level 1 over lambda tilde, then the power allocated is 0, right, because 1 over lambda tilde minus sigma square over sigma t square is negative, right. In this case, if you look at this, 1 over lambda tilde minus sigma square over sigma t square less than 0 implies Pt equal to 0, implies the transfer power. So, power is allocated only if sigma square or sigma I square is less than the water level 1 over lambda. This is important. So, power is non-zero, Pi is not equal to 0 only if sigma square over sigma I square is less than 1 over lambda tilde. What is this 1 over lambda tilde? This is basically your water level, and this algorithm is known as the water filling algorithm. So, you can think of this Pi equal to 1 over lambda tilde minus sigma square over sigma I square, right, sigma I square plus as the water above the bar, water height above bar, and this is essentially, therefore, this is termed as the water filling algorithm. This is basically this is a very celebrated, very popular algorithm for optimal power allocation. This is termed as the water filling algorithm, right, water filling algorithm for optimal power allocation, to allocate the power to maximize the sum rate, or to maximize the to achieve the capacity of the Mimo system. Okay. So, what does the water filling algorithm do? Water filling algorithm it allocates the powers to the sub channels optimally. So, this is allocates, this is for optimal power allocation, which implies this achieves the Mimo, this achieves the capacity of the Mimo channel. Okay. So, this is basically the water filling algorithm leads to optimal power allocation, which achieves the capacity of the Mimo channel. Okay. So, therefore, that is essentially how the SVD can be used to maximize the rate of the Mimo system, and then therefore, the SVD indeed you can see has is a very important tool for optimization of the performance, right. So, SVD can be used to decouple the Mimo system, convert this coupled Mimo system into decoupled Mimo systems, that is the T parallel channels, transmitting independent symbols x1 tilde, x2 tilde, x3 tilde, right. And now you can use the rate maximization framework to allocate the powers in an optimal fashion, so that subject to a total available power P naught, using that is subject to this total power constraint P naught, the sum rate, the rate at which you can transmit information reliably over this MIMO channel, multiple input multiple output wireless channel, is maximized. And in fact, as we have seen, MIMO is a very important technology both in 5G, 4G and 5G, which helps achieve incredibly high rates to the tune of several hundred megabit per second, and in fact in 5G going up to gigabit per second. So, MIMO technology in MIMO can be used both in 4G and 5G and 100 megabit per second and gigabit per second in 5G. So, essentially it is a very important this is a very important technology. Okay. Let us look at a simple example for MIMO optimization. Let us look at a very simple example for MIMO optimization. Consider the channel (1, 2, -2, 2). This is our MIMO channel. Recall, we have already seen this before. This is recall 4x2 MIMO channel, which means the number of receive antennas equals 4, number of transmit antennas equals 2. Let us now say in this system the noise power sigma square is equal to 16, total power P naught is equal to 5, and now we want to ask the question, determine the optimal power allocation. Okay, so we want to determine the optimal power allocation for this system, and for that we begin with the SVD, and recall we have already performed the SVD of this in a previous example, and the SVD of the channel matrix, right, based on the property that the columns of H are orthogonal, right. We have already evaluated the SVD of this. You can look at the previous module, and the SVD of this is given as half minus half minus half 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 times the singular values matrix of singular values, that is 4 0 0 2 times 0 1 1 0, which is the matrix V Hermitian, and remember these are the singular values. So, if you look at this is basically your matrix sigma, which is the diagonal matrix of singular values. So, this is given as 4 0 0 2, and therefore, the singular values are sigma 1 equal to 4, this is sigma 2 equal to 2, and Therefore, now the optimal powers are given as P1 equals 1 over lambda tilde minus sigma square over sigma 1 square, which is 1 over lambda tilde minus sigma square, that is 16 over sigma 1 square, that is 16. So, this is 1 over lambda tilde minus 1. Of course, it is equal to this quantity only if it is greater than equal to 0. If it is less than 0, then it will be 0. Alright. So, we have to determine that. And P2 equals 1 over lambda tilde minus sigma square over sigma 2 square, which is 1 over lambda tilde minus 16 divided by lambda tilde. What is lambda? 16 minus sigma 2 square, which is 2 square, which is 4. So, 1 over lambda tilde minus 4. Now, we must have P1 plus P2 equal to P naught, which is equal to 5. Remember, this is our total power constraint. This is, remember, our which basically implies 1 over lambda tilde minus 1 plus 1 over lambda tilde minus 4 is equal to 5, which basically implies that 1 over lambda tilde equals, or 2 over lambda tilde, I am sorry, 2 over lambda tilde equals 10, which basically implies 1 over lambda tilde is equal to 5, right. So, that is essentially what we get, and therefore, we get P1 substituting back, we get P1 equal to 1 over lambda tilde minus 1, which is equal to 5 minus 1 equal to 4. This is greater than equal to 0. So, and P2 equals 1 over lambda tilde minus 4 equals 5 minus 4 equals 1, which is also greater than equal to 0. Both these values are non-negative. So, this is a valid power allocation. Remember, because the power values have to be non-negative, otherwise you have to set the corresponding power to be 0. If it is negative, you have to set the corresponding power to be 0, and then you have to do the problem again. Okay. So, essentially this implies that P1 is equal to 4, P2 is equal to 1, and this therefore is basically our optimal Mimo power allocation for rate maximization. This is essentially the optimal power allocation, which is given by the water filling algorithm. Alright. So, this is a very, very interesting and I would say a very high impact application of the singular value decomposition. You start with the Mimo channel, convert it into a decoupled channel, right. Look at what is the output SNR for each channel, ask what is the output rate, maximum transmission rate, and look at what is the sum rate, right, and then maximize this sum rate subject to the transmit power constraint, that is P naught, and the optimal powers are given by the water filling algorithm, and we have also seen an example to understand this water filling power allocation in action, and evaluated the powers, right, the transmit powers of the individual channels, right, the component channels of this Mimo channel to maximize the sum rate, that is to achieve the Mimo capacity. All right. So, let us stop here and let us continue with this discussion in the subsequent modules. Thank you very much.